Hi everyone, and welcome to today's webinar, where we'll dive into securing enterprise JavaScript applications, especially focusing on JavaScript's inherent security vulnerabilities and how to properly mitigate them. I want to start by letting you know that this webinar has been pre-recorded, so if you have any questions, you can reach out to us at hello@jscrambler.com and we'll gladly answer them. Joining us today, we have Randall Swart, who is the North American Sales Director at JScrambler. Randall has over 20 years of experience working in the software industry and a track record in the native code protection space. Today, he works closely with enterprises from sectors such as finance, broadcasting, and e-commerce in helping them improve their web application security. Thank you for joining us, Randall, and the floor is yours.
Thank you, Felipe, for the introduction, and I really appreciate being here today, focusing on this very relevant topic of JavaScript security in the enterprise. If you're working with JavaScript, it's entirely likely that you are familiar with its history. JavaScript turned 24 this year, and when we look back at these past 10 years, we see just how drastically it's changed, especially when Node.js entered the scene, along with JS frameworks such as jQuery, and later on React and Company. The JavaScript open source community truly has changed the language. If in 2009 you used JavaScript mainly as a way to make your website more dynamic and enjoyable, in 2019 JavaScript is the backbone of your web, mobile, and even desktop apps. It paved the way to highly advanced services such as streaming, online gaming, and has unlocked new business models in sectors like banking, e-commerce, and healthcare. If we put this into numbers, we see that 97% of modern web apps use JavaScript, and every single Fortune 500 company relies on Node.js and JavaScript to create highly competitive applications. And as I mentioned before, today JavaScript isn't confined to a browser on the web. With cross-platform frameworks like React Native and with progressive web apps marching towards mass adoption, companies can cut their development time and costs significantly by reusing a shared code base for web, mobile, and desktop. But even with all its numerous advantages and business value, we still must consider the other side of the coin, the considerable security threats linked to using JavaScript, especially in commercial or enterprise applications. Usually, when we mention JavaScript security, the first things that pop up in our minds are security testing tools like SAST and DAST. These are widely used to inspect the application source code, check if it contains any vulnerabilities, and attempt to fix them. Considering that the typical JavaScript application today has well over 1,000 code dependencies and an absolute mess of sub-dependencies, development teams need SAST and DAST to gain visibility over potential code insecurities. However, if we find and fix every single vulnerability in our JavaScript code, at the end of the day, there is something that really doesn't change. JavaScript is still very easy to understand. At first, this might sound silly, but let's not forget, just like we can look at our code and understand how applications work, so can an attacker. And here we must ask ourselves, do we have any proprietary logic running on the client side? What would it cost us if someone was to retrieve an important part of our code? Or bypass some of our application's restrictions, or even tamper with our code to exfiltrate our users' data. These questions lead us to uncover the real threats posed by having our JavaScript code completely exposed. There are quite a few, and today I'll be focusing on some of the most relevant ones when we're dealing with commercial or enterprise JavaScript applications. And the first threat on my list is that of automated abuse. When you have exposed JavaScript, you open the door to application abuse, which, in the context of the web, means exploiting the application's functionalities to gain illegitimate access or privileges, mainly through the use of bots. For instance, If you're a cloud provider, you may offer 1 month free for new accounts. This can be abused by malicious actors through automated account creation, for instance, to mine cryptocurrencies. In these cases, CAPTCHAs can also be used, but it is not uncommon for these service providers to avoid relying on CAPTCHAs, as they sometimes create a barrier for real legitimate users. Then we have the special case of JavaScript agents. These are often deployed to control account takeover and fight off fraud, namely by stopping bots or providing device fingerprinting. A real-life example is the use of agents to detect bots, specifically by large retailers with limited product collections. The bots track new collection releases in order to grant attackers an advantage over other users. To fight this, companies are currently deploying algorithms for bot recognition. However, because these algorithms run partially on the client side, attackers can access that source code and therefore can tamper with them, avoiding detection. In gaming, a big problem is cheating, which is caused in part by exposed JavaScript in HTML5 games and even native game clients that use JavaScript. Attackers can take advantage of exposed JavaScript to tamper with it and gain access to a game without paying, as well as unlocking new features, content, or in-game assets. This gives an attacker or user of these cheats an unfair advantage in the game over others, which of course creates a serious problem for the game publisher and directly impacts their revenue. Piracy is similar to cheating in the sense that the attacker needs to be able to tamper with the application code successfully. However, in this case, the attack aims to remove licensing restrictions and anti-cheating defenses to allow the attacker to distribute a pirated version of the application. Once again, this can severely impact the business model and revenue of the company that built the application. Piracy is especially important in digital content delivered through web video players and streaming services. By accessing the underlying JavaScript of HTML5 web players, attackers can easily capture and redistribute streams. Stream capturing can be a cause for concern for different reasons. First, because the content could be copyrighted, and so the stream providers could be liable. Second, it can cause revenue loss due to a drop in paid subscriptions. Third, because bandwidth can be stolen if attackers manage to embed the stream in unauthorized websites. In highly valuable digital content such as live sports or premium content, it is crucial to quickly block users that leak content. Many content owners demand that client-side watermarking be used to protect that streamed content. But techniques like this also partially run on the client side, and therefore this logic can be accessed and tampered with if not protected. The same reasoning leads us to the issue of intellectual property theft. While common knowledge dictates that the code secrets or sensitive code must be kept on trusted execution environments such as backend servers, much like what happens in streaming, some services have algorithms that must be executed in untrusted environments like the client side. This may happen because there's not a backend in the first place, as in the case of mobile applications. But performance is probably the most common reason to ship code to the client side. Some code might even be related to the end user experience, and for that reason, must be on the client side. Whatever the case is, at the end of the day, companies don't want to expose their proprietary logic or code secrets and risk it being reverse engineered by competitors or other third parties. However, we must remember that unless we do something to protect it, client-side JavaScript can easily be accessed and compromised. And to close the list of main threats of exposed JavaScript, we have what is likely the biggest concern in web security today: data exfiltration. Data exfiltration as a whole is an extremely complex issue, and I won't obviously be covering the whole of it. However, what I will do is focus on the side that comes out of the issue of exposed JavaScript. As an internet user, you have surely submitted data like your email, name, address, credit card number, or even medical information in a website using a form. And as we know, the logic behind these forms is handled by JavaScript. so all this sensitive data will pass through the client side at some point in time. You have probably already guessed where I'm going with this. If this same client-side JavaScript isn't somehow protected, attackers are given a free pass to tamper with it and can use this as another way to capture sensitive data. In critical applications in sectors like healthcare, banking, defense, or e-commerce, this gains increased importance as these industries often have standards and regulations that they have to be in compliance with, and that requires this code not to be exposed in a way to prevent data exfiltration and intellectual property theft. So as we saw, having client-side JavaScript completely exposed can result in a number of security complications in commercial or enterprise applications. These can mean disastrous losses, both in terms of revenue, brand, and even harming the well-being of their end users, who may stop using the application after an attack. So it only makes sense to keep JavaScript secure and hidden away from prying eyes. Ideally, we would either encrypt the JavaScript or simply have no JavaScript on the client side at all. But, as I will explain, neither of these are a feasible option. Encrypting JavaScript doesn't really work because the browser always needs to render JavaScript so that it works. If we have a decryption key, we need to supply that to the browser, and that key can be compromised, so then the code would be easily accessed. As for keeping no JavaScript on the client side, a key issue here is that the server calls take time, and in services where performance is crucial, such as streaming, e-commerce, or gaming, storing all that JavaScript on the server just isn't an option. So it may seem that we're left out of options. Since we really can't prevent attackers from accessing our client-side JavaScript, what can we do to make our JavaScript really hard to understand, while also preventing attackers from debugging or tampering with our code? This is actually a security recommendation by OWASP on their mobile top 10 security risks, precisely because of the underlying dangers of exposed JavaScript. Now let's take a look at how we can actually protect your client-side JavaScript in HTML5. Typically, one of the things we want to achieve is to transform our source code into something that's completely unintelligible, but that can still be interpreted by the browser just like the original code. This can be achieved by JavaScript obfuscation and transformation. This security layer includes a series of code transformations that turns your exposed code into a protected version of the code that is extremely hard to understand and reverse engineer. This should not be mistaken with minification, which is solely optimizing the code, or encryption, as there is no password to decrypt the obfuscated code. While JavaScript obfuscation is a term used broadly to describe JavaScript concealment, the obfuscation result and its actual security greatly depends on the tool or the techniques used. Free obfuscators offer very basic transformations which may be enough for personal or non-commercial projects, but they can easily be reversed using automated tools. Then different commercial tools also provide vastly different levels of obfuscation techniques, with most also being reversible with automated tools. Because of this vast difference between different obfuscation tools, it is important to refer to the metrics that can actually measure if a certain transformation or set of transformations offer good enough protection or not. Most peer-backed metrics to evaluate transformations are potency, resilience, and cost. Potency measures how difficult it is for a human to understand the obfuscated code when compared to the original code. This can be calculated using specific software, and the resulting metrics allows us to determine the impact of the transformations in the code. For example, JScrambler's technology can be used to achieve high potency with transformations to strings, variables, functions, and objects through the advanced logic concealing techniques that also obfuscate the program's control flow. Resilience measures the difficulty to revert the transformed code to its original form. Resilience goes hand in hand with potency, since some of the transformations may fool humans reading the code, but can easily be reversed by a deobfuscator. An example would be adding an if statement which introduces a dummy variable. A human might not be able to identify the code as dummy code, whereas a deobfuscator would easily be able to remove the statement. Resilience is calculated by considering the amount of time required to develop a deobfuscator capable of reverting to a transformed result and the required execution time and space by a deobfuscator to effectively revert the transformation. This is the metric where most obfuscation tools come too short. JScrambler's transformations, however, are built to achieve maximum resilience whenever possible. JScrambler's code hardening feature is built into every code obfuscation and grants the code with guaranteed up-to-date resilience against all automated reverse engineering tools and techniques. Finally, we have the cost metric, which represents the impact of a given transformation in the execution time of a transformed application, as well as the impact on the application's file size. This is especially important because you wouldn't want your application performance to be ruined due to adding security and obfuscation. So, an enterprise tool like JScrambler provides specific capabilities to keep performance hits to a minimum, namely by leveraging code annotations which enable you to control which specific transformations you want to use in the specific parts of your code. Understanding these three metrics is very important to ensure that your code is actually protected and doesn't just look like it is. I usually like to give this very interesting example of a piece of code that has non-alphanumeric obfuscation, which you don't find often in the wild. While the potency of this obfuscation is high, as it seems impossible for a human to understand the obfuscated code, the obfuscation is actually very weak. It has almost zero resilience because it is very easy to defeat using an eval poisoning attack. So with this tool here, I can modify the eval function and it just dumps whatever goes through the eval. When I click deobfuscate, it returns the original code, which is simply alert 1. So we were able to defeat this obfuscation in a single step. And so a key takeaway here is that just because a piece of obfuscated code seems extremely hard to understand, it doesn't mean that the obfuscation is good unless it's also resilient. Getting back to our original train of thought, we can see that the enterprise-grade obfuscation for JavaScript should include a balance of transformations that, when combined, provide good potency and resilience while not resulting in a high cost. This should grant the application a good level of protection against code theft and reverse engineering. But we must still consider one more advanced and dangerous threat of application abuse, cheating, piracy, and data exfiltration. Again, the enterprise-grade problems require enterprise-grade solutions. To ensure that all these targets are covered, JavaScript protection must go beyond obfuscation and include additional security layers. One of these more advanced layers is code locks. These, which are also known as application locks, enable us to lock our JavaScript to only execute in predefined environments. As so, it gives us the ability to prevent our code from running in undesired settings. Some possible JavaScript locks include the operating system, browser, domain, as well as dates. These unlock new possibilities, namely to enforce licensing agreements. You can, for example, deliver a product demo to a client and have that code automatically expire after a set date. With code locks on top of JavaScript obfuscation, we're one step closer to effectively mitigating these serious threats of piracy and abuse. But even so, if an attacker is motivated enough, tinkering with the code in runtime to relentlessly seek to understand the underlying logic, additional layers may still be necessary. And here is where self-defending, also known as client-side RASP, comes into place. As the name implies, this security layer brings JavaScript protection to the runtime application. Like I mentioned before, a relentless attacker may try to understand the code logic of our obfuscated code by debugging it and experimenting with it in runtime to gradually understand portions of the code. RASP will prevent this altogether. First, it gives the source code the ability to detect when a browser debugger is open and breaks the application immediately, preventing dynamic analysis. Second, it scatters the integrity checks throughout the entire protected code base, so that whenever a piece of code is changed, the application also breaks. This prevents static analysis and reverse engineering of the protected code. With RASP as a third layer of security, we make it completely unprofitable for attackers to understand or tamper with our code. We can still go one step further by making our code trigger an automatic reaction whenever somebody attempts to violate a lock, or debug the code, or tamper with it. As I mentioned, by default, you want your application to break as a response to an attack in runtime, but there are several scenarios where it's valuable to trigger other countermeasures. An example is redirecting the attacker to another page, with the objective of making the attacker lose all progress. Another valuable action would be to issue a custom callback to your SIEM, with the goal of sending an immediate alert to your security team. More advanced countermeasures can be used to give you increased visibility over every attempt to debug or tamper with your code, such as providing you with real-time notifications every time that one of these attacks is blocked. And this is actually my cue to show you all of these security layers in action when you protect your own application using JScrambler technology. In this demo, I'll impersonate an attacker trying to cheat in an HTML5 game by tampering with the source code. However, this source code is protected with JScrambler. This HTML5 game is built using Construct2 framework, which is a pretty common framework in the gaming sector. However, JScrambler is compliant with all JavaScript frameworks, so as long as it's JavaScript, we're able to protect it. Now I'm going to impersonate an attacker, and my goal could be, for example, to steal the code and monetize it elsewhere, or to cheat for leaderboard purposes, or even to avoid payment. And if I'm trying to mess with the application, I would try to understand the code and its logic dynamically at runtime. A good tool to do this is, for example, the Chrome debugger, which is useful for debugging the application. So I will open the DevTools and get it started. As you can see, the application stops and you won't be able to resume it again. Even if I try to resume the execution without breakpoints, you can see that the call stack is piling up. But I'm always stuck on the debugger loop. This is happening because JScrambler gave the code anti-debugging capabilities. Let's perform a step-by-step inspection of this purchase button, which would be charging my account if I decided to purchase extra rockets. We're going to select Event Listeners and then click. Now I'm able to see some information. Let's just pretty print the code to look at in more detail. Now I can see some code, but it is highly obfuscated. So I'm going to select some random breakpoints to perform a step-by-step inspection. However, if I do that, the call stack starts to grow. And again, I'm stuck in an infinite loop. A good thing is that the application's save state is easily resumed by simply closing the debugger, not interfering with the end user's experience, in case it was an unintended action by the user. Getting back into the shoes of an attacker, my next step would be to statically analyze to understand the code, possibly even try to reverse engineer it. In this case, I already have the code on my machine, so my job is simplified. First of all, I'm going to present an unprotected version of this game. You can really understand the flow of the application, any strings, and functions among it. After being protected by JScrambler, the same application looks like this. You can see that the code is heavily obfuscated, and it's not recognizable JavaScript anymore because it is protected with several of JScrambler's obfuscation transformations. Coming back as an attacker, even though I can't understand the code, I would try to discover a function here such as eval. I can see that there is an eval function here, and I would make an assumption that whatever variable is being fed to the eval function, it will probably take me back to the original code. So I try to console log the content of the variable x. Now I'm going to save the application and run it again. As you can see, the application simply breaks. This happened because of the anti-tampering capabilities that JScrambler provides to the application. JScrambler scatters integrity checks through the application so that it can detect if its original functionality has been tampered with. Let's again open the debugger and see what was dumped to the console. The only thing that I get from the eval function is just trash and broken references. Now that we have seen how the application reacts to an attack, let me just give you a brief overview of how you would actually use JScrambler to protect your JavaScript source code. This is the JScrambler application dashboard. This is where you'll be able to manage your applications and see their protection history. We have recently launched a new feature that we call threat monitoring, which provides you visibility on what is happening on the client side in real time. If we click on our Space Shooter application and then App Live Feed, you'll be able to see a real-time list of malicious events that happened on the client side. You can see that we have several alerts for a debugger that was opened, and also that self-defending capabilities were triggered. These events correspond to our previous attacks while we were impersonating an attacker. And by clicking on one of these events, you can check more details such as the IP address of the attacker and the user agent. Let's come back again to the code integrity dashboard to protect our source code. On the left side, you can see your file tree, and by clicking on each file, you'll be able to preview the source code. In the middle of the screen, you can see the original source code and outputted protection code, enabling you to compare the differences after protection. On the right side of the screen, you can see and change the application settings to better match to your use case. Here, you'll be able to select which JavaScript specification you'll be using and the application type. Then you can select one of the predefined protection templates. These work like a cocktail of transformations that you can apply to protect your source code with a specific goal in mind. Another option is to go to the Fine-Tuning tab to pick transformations one by one. By clicking on Advanced Options, you can see a list of transformations organized by the obfuscation type, code locks, and self-defending layers. Because it's not expected that you're an expert on JavaScript transformations, you can read a brief description for each and find a link to their documentation. I already chose some transformations to show you how you would do this protection and what the code looks like after being protected. So I'll go ahead and click on Protect App, and in a few seconds, I have a new version of the protected code. Another relevant aspect of how JScrambler protects JavaScript code is that it has polymorphic behavior. This means that even when you select the same set of transformations, the protected version will always be different. In this demo, I won't be showing you how to use the JScrambler API to protect this code, but it's a very simple process where you would use this JSON file with all of JScrambler's configurations. With this, you can easily integrate JScrambler into your build process by using one of our API clients such as Webpack, Ember, Grunt, Gulp, and Node.js. The way we ship the process is in a virtual appliance that you download and run in your own infrastructure, which means that you never have to send us any of your source code. JScrambler also has integrations with all the main frameworks like React, React Native, Angular, Vue, and many others, so that you protect your code seamlessly at build time. We're now ready to wrap up this webinar with today's main takeaways. And as we start with the main problem, JavaScript is everywhere, but by default it is exposed, opening the door to attacks. By freely accessing and easily understanding an application's source code, attackers can retrieve proprietary logic and threaten a company's competitive advantage. When we add to the equation an attacker's ability to tamper with this code, we must consider more serious attacks like automated abuse, cheating, piracy, and data exfiltration. Commercial and enterprise JavaScript applications require a multi-layered approach solution that provides potent and resilient obfuscation, along with code locks and runtime self-protection. JScrambler provides this cutting-edge protection along with real-time threat monitoring for maximum visibility of client-side attacks. And, as you would want in an enterprise-grade solution, It provides support from a team of experts in JavaScript and application security.
Thank you, Randall, for your detailed explanation. I want to remind everyone that you'll receive an email with our datasheet on JavaScript security threats, which gives an overview of what we discussed today in just 4 pages. As I mentioned earlier, if you have any specific questions, feel free to reach out to us using the email you see here. Don't forget that you can also schedule a one-on-one meeting with one of JScrambler's application security experts, in case you want to discuss how JScrambler can help with your own use case. Just send us an email or follow the link you see here. And that's it for me. Thank you for joining us and make sure to protect your web apps.